Right, we're going to have a look at the theorem L13.2, which is the Bolzano Cauchy for uniform convergence theorem. Now, as before, we have very few assumptions indeed. The only thing we assume that is that we have a sequence, an infinite sequence, of functions fn such that they map some interval j onto the real number line. Then, there exists some function f such that fn converge uniformly to it on j, and this holds if and only if, so we have a biconditional here, if and only if for all epsilon greater than 0 there exists some capital N natural for all n m greater or equal to the capital N for all x in j, such that the difference of fn of x and fm of x is smaller than epsilon. So this indeed is just the Bolzano Cauchy criterion. The only difference is the position of one quantifier, as this one. In the classical version, this quantifier is right at the beginning here, but we have moved it down here, which has made this a much stronger claim. Now, the proof is trivial. Let us begin with the first implication. So, we assume that for all epsilon greater than 0, there exists some natural n, such that for all n greater or equal than it, and for all x in j, in other words, we are assuming the uniform convergence of fn to f on j, fn of x and f of x, that difference is smaller than epsilon. Splendid. So we have found such n. We know that it exists by assumption. Then, for all m natural and for all n natural, the difference of fn of x and fm of x is smaller or equal to, by the triangle inequality, than the difference of f of x and fn of x and the difference of f of x and the fm of x. But of course, it follows from here that this is smaller than 2 epsilon, which is precisely what we wanted. So, we have proven the first implication, and let's have a look at the other one. This one is similarly easy. So, we assume that for all epsilon greater than 0, there exists some capital N natural for all n m greater or equal to than n, to n, for all x on j, fn of x and fm of x differ by no more than epsilon. Suppose we fixed x. So, fix x. Then, by the classical Bolzano Cauchy criterion, Fn of x has a limit and it approaches some an. In this fashion, we can construct a function f of x, which we define as the limit as n approaches infinity of fn of x. And we know that this limit exists precisely by the Bolzano Cauchy Criterion, the classical version, which we are using here for the fixed x. And now we simply say that as n approaches infinity, this becomes our claim for all epsilon greater than 0. There exists some natural n for all, well, as m approaches infinity, for all n greater or equal to than n, to n, and for all x. Fn of x, f of x, their difference is no more than epsilon, which is precisely what we wanted. This means this is equivalent to saying that Fn converge uniformly to f on J.